So today is actually the last lecture, okay, of this semester for this class, okay. I'm happy that we have more students today, okay, compared with last week especially, yeah. Okay, anyway, just want to remind you again, okay, we will have final exam next week, and the sample final has been provided in E-class, okay. We will also have the final project presentation at the in the final exam week, okay. So after the final project presentation, when each group finish the presentation, I will give some comments, and you could base on my comments to, well, if it's great, just basically just write your report, okay. If I have some comments, maybe you need to do some more work and write a report, and then you have to turn in the report, I think like 6 days, okay, after the presentation. The reason is 6 days, not 7. It's not a week. It's because I have to turn in the grade like a week after the presentation. So I have to get your report like at least 1 day in advance, so that I can have some time to do the grading. Okay. Just for your information, the grading of your presentation and the final report, for the term project, is done by me, okay, not by the TA, okay. So just want to remind you all this, okay. So let's get started. Last time we talked about the Sparse autoencoder. We talked about 2 ways to create the Sparse autoencoder. The first one is to use Regularizer, okay. But that one may not provide what we want it to be, okay. The second one is what we are talking about here, okay. So and we talked about the KLDivergence last time, okay. And I actually spent a little bit of time to talk about what's the true application of the KLDivergence. Here we use it, just because, this formula can provide us like more gradients, which allowed us to have a faster convergence, okay, when we train the model, okay. But we didn't finish this part last time, okay. So yeah, so we will try to finish this one, and I think if we are lucky, I think we should be able to do that, okay. We will also talk about another autoencoder, and then move on to talk about the GAN, okay. Even though I do not anticipate, as I mentioned earlier, okay, the final exam, okay, will cover everything I have told in this class up to the end of autoencoder, but not the GAN, because GAN I'm probably only going to start the topic, okay. Maybe I will have time to talk about one example, but that's about it. But actually, GAN is much more difficult than what the first example can reveal. Okay, so I think like it's probably not fair to talk about, to cover GAN in a final exam. So, but just for your information, okay, the more important things, the final exam, okay, cover everything up to autoencoder, okay? So, okay, back to this topic, okay? So, so once we compute the sparsity loss for each neuron, okay, the second approach is you compute this sparsity loss for each neuron. You basically check like how frequently, okay, each neuron is activated, okay, you know, compared with the target, you know, your target frequency. Maybe you want it to be activated only like 1% of the time, okay? But if this neuron activates too much, for example, like higher than that frequency, during one batch, okay? So we basically compute like you know, the frequency of activation for each neuron during one batch. That batch normally is assumed to be a little bit larger, so that I mean that frequency, okay, is representative, okay. So anyway, so we sum up. So we basically compute the sparsity loss for each neuron. So if it's like if it's different from the target sparsity, we basically, you know, will penalize, or add a certain cost to the cost function. So that's like what we call sparsity loss. So we sum up these losses and add the result to the cost function, as I mentioned. So to control the relative importance of the sparsity loss and the reconstruction loss. Remember, I mean, the loss function for the autoencoder is the reconstruction loss. Okay, but now for this particular sparse autoencoder, we have another sparsity loss, right? So we have two losses in the cost function. Okay, so we can multiply the sparsity loss by a sparsity weight hyperparameter. Okay, so what is this sparsity weight hyperparameter? Okay, if this weight is too high, okay, then we will stick closely to the target sparsity. Okay, but it means we focus on this sparsity requirement, but the reconstruction may not look good because, well, since we focus on the sparsity loss, okay, in this case. But you know, on the other hand, okay, if we set this sparsity weight hyperparameter too low, okay, the model will probably ignore the sparsity objective, okay, meaning like you will see a lot of neurons, you know, that their activate frequency is, you know, it's not very close to the target sparsity target. Okay, so it will not learn any interesting features because, well, this sparsity requirement is the constraint we set to this autoencoder. Okay, remember we set a constraint for autoencoder to learn something, right? So if you don't set the constraint enough, then this autoencoder will just try to reconstruct the input to the output. I mean, just copy the input to the output, and it will not learn, I mean, interesting features. Okay, so this is like how we implement the sparse autoencoder. Okay, so just we first like you know, create a custom regularizer. Okay, this custom regularizer is to apply the KLDivergence regularization. Okay, so I think this is pretty straightforward. the only thing I want to remind you is this one. Return this. Okay, this looks so complicated. This is basically this thing basically summarize this function. Okay, so that's why I mean it looks like a complicated, but actually this is just KLDivergence computation. Okay, very straightforward. Okay, so once you have that defined, okay, we can build the sparse autoencoder by means of this KLDivergence regularizer. Okay, so in here, okay, still we are assuming we are using the fashion MNIST data set. So first we set our KLDivergence regularizer. Okay, we set it to be the weight to be 0.05, target to be 0.1. This target means like the target sparsity. Okay, we want each neuron to be activated only 10% of the time. Okay, and the weight refers to the sparsity loss weight hyperparameter. Remember I talked about that. I mean, this value cannot be too high, cannot be too low. Okay, it's not like something at 0.5. Okay, or like it's not like that. It's actually like much lower than you may think. Okay, 0.05, which is already quite strong. Okay, if you see the result, okay, you will see that. Okay, after all, for autoencoder, the more focus will still be put on the reconstruction. Okay, so we have this created. Okay, and then okay, we use the sequential API. Okay, so we flatten the input. Okay, which is 28 by 28. Okay, I think this is like nothing new. Okay, and we have this 100 neuron redo activation, and then our coding. Okay, is 300 neuron. Okay, this and we use sigmoid activation. Okay, and in here, okay, we set the activity regularizer to be KLDreg. Okay, so we use this to regularize the activity of these neurons. Okay, these 300 neurons. Okay, and the reason to set it to be sigmoid is because this one will output between 0 and 1, right? So remember, we want each neuron to represent certain feature. Okay, so I mean each neuron represents, okay, this feature is on or off. Okay, when it's close to 1, it means this feature is on. When it's close to 0, it means the feature is off. So that's why I mean the activation function for this particular example is sigmoid. Okay, and then for decoder, I mean it's very straightforward. Okay, so it's a C rule. Okay, then well, input shape is 300. I mean the coding is 300 dimension. Okay, and it's 100 neuron, just like it's symmetric to this layer. Okay, and then we have this layer which is symmetric to this one. To this one. Okay, but we use sigmoid activation. Okay, remember because we treat each pixel as a binary classifier for the reconstruction of this facial MNIST image. Okay, if you still remember, we talked about this. Okay, so this is still basically the same as like what we have earlier. Okay, and then we reshape it into 28 by 28, and then okay, so we can we combine the sparse KLEncoder and the sparse KLDecoder to form our sparse KL autoencoder, like this. Okay, that's it. Okay, and one thing interesting is that okay, if you train this sparse autoencoder on fashion MNIST data set, okay, the activation of the neuron in the coding layer are mostly close to 0. Okay, about 70% of the activations are lower than 0.1, lower than the target sparsity. Okay, and all neurons have a mean activation around 0.1. So it's actually this means we have achieved our goal. Okay, so about 90% of all neurons have a mean activation between 0.1 and 0.2. Okay, so this is the statistics. Okay, we draw it into a figure. Okay, just for you to see. Okay, the x-axis is like this one is for the activation. Okay, y-axis is for the percentage of activation. Okay, for this figure is the x-axis is a neuron mean activation, which is basically what we intend to achieve is 0.1, right? And so number of neurons for this for their like mean activation, you can see. Okay, some of them are between 0 to 0.1. Most of them are between 0.1 to 0.2, but the average is very close to 0.1. Okay, and this is the distribution. It's a long tail distribution. I mean, but it's obviously like a case because, well, you couldn't be lower than zero frequency, right? So it must truncate. I mean, on the left-hand side, but because of this long tail, so you can see from 0.1 to 0.2 is a little bit higher, but the average is still like 0.1. Okay. So that's the sparse autoencoder. Okay, which has a very special application. Okay, and then. Okay. Oh, by the way, the sparse autoencoder, the most important application for that is to visualize your what the feature is represented in your data set. Okay. So it is basically for like a data visualization purpose. Okay. And then we are going to talk about the last example of autoencoder, which is called variational autoencoder. Okay, so this variational autoencoder, okay, is a very important category. Okay, it was introduced in 2013. Okay, by these two researchers. Okay, and it quickly became one of the most popular types of autoencoder. Okay. Why is that? Okay, it's because they are different from the autoencoders that we have introduced so far. Okay, in two different points. Okay, the first point is they are probabilistic autoencoders. Okay, meaning if you feed in the same data, okay, it will output, each time it will output slightly different output. Okay, so far, all the autoencoder we have discussed, okay, if you give it like a certain input, it will always give the same output. Okay, so the autoencoder is pretty much deterministic. Of course, like you could incorporate like dropout, right, in the autoencoder, and the dropout, you may say, oh, dropout incorporates certain probability into the model, right? But the dropout only work during training. After the training, when you use the autoencoder for inference, okay, basically whatever you put in, the output is fixed. Okay, you cannot like feed in like one output and expect it to output like two different things. I mean, for the past examples of autoencoder that we have discussed. Okay, but this variational autoencoder is different. okay? I mean, because it's probabilistic nature, okay? We'll talk about that, I mean, shortly, okay? The more important thing, why this variational autoencoder is popular, okay, is important, okay, is because, okay, this autoencoder is what we call generative autoencoder. Okay, what do I mean by generative autoencoder? I mean, if you provide, certain stuff to it, okay, it's going to help you to generate new data. Okay. Of course, I mean, if it does a good job, okay, you can even use that data for maybe, for example, to train a model or something like that. But you will see that, I mean, although this is a biggest advantage of but because like right after this variational autoencoder was introduced, like a few years, actually like just another year, I think, like the GAN model was introduced, and after a few years, people find out that GAN is much better at generating new data for us, okay, and so the variational autoencoder is at least in terms of generating the training data, okay, the variational autoencoder is no longer that important. But you still see variational autoencoder used in many applications, including, for example, like in my lab, we are doing autonomous driving, and one model that we use to detect, like to predict, like the path of vehicles, okay, is variational autoencoder. Okay, so this thing is like a very even for now, okay, it still has a lot of application. Okay, so let's have a look at this variational autoencoder. So okay. The property of variational autoencoder, okay, are similar to restricted Boltzmann machine, okay, but they are still very different, okay, because we talk about the variational restricted Boltzmann machine, okay, you need to wait for the machine to stabilize to do the sampling process, and then after the sampling process, you have to wait for it to stabilize again, okay. To reach what we call like a thermal equilibrium, okay, before we can sample again. So this is very inconvenient, okay, it takes a long time. And so variational autoencoder perform variational Bayesian inference, okay. We didn't talk about the chapter 9. If you are interested, I mean, you can actually check out the chapter 9, like the content, to learn more about variational Bayesian inference, okay? So it's an effective way to perform approximate Bayesian inference. I mean, if you are more interested in Bayesian inference, by the way, I mean, I teach Bayesian data analysis. I mean, but not next semester, maybe like next year, okay? Because I have taught that class too many times, so I kind of feel like I want to switch, like do some switch. So next semester I'm teaching computational geometry, but the next year I'm going to teach Bayesian data analysis again. So if you are interested in this topic, I mean, assuming next year you are still here, you are more than welcome to take my class. Okay, so how variational autoencoder works? Okay. So let's see this one. Okay. So the variational autoencoder is going to take the input, and of course it's going to go through certain hidden layers, but the coding is very different. The coding is very different. Okay, in the past, we normally see like a coding vector, right? Like where you output like maybe like a 30 vector of 30 dimension, something like that. Okay, but now this one is like we will output two things. Of course, each of them will still be a vector. Okay, I'm not saying the vector is not used, but I'm saying like the vector, the coding, okay, use vector in a different manner. Okay, because now, okay, we have a mu, we have a sigma. Okay, and so this mu and the sigma is going to transform your input into another space. Okay, assuming your input, okay, all your data, okay, after transformation is going to map into certain space like this. Okay, each instance will be a point in this space. Okay, and this coding mu and this coding sigma basically is saying like okay, we map this instance into a Gaussian distribution. Okay, where mu represent the mean and the sigma represent the variation or standard deviation. Standard deviation. Okay, so for example, in a two-dimensional situation, of course, you may say, oh, so this is this the space two-dimensional? Unfortunately, they are not two-dimensional, but we draw it as a two-dimensional so that you can have a better understand. Okay, but as I have told you, okay, this coding and this mu and the sigma are not necessarily two-dimensional. As I say, they are vector, right? Okay, so maybe like they are, let's say, for example, 30 dimension. Then your coding space will be 30 dimension. Okay, 30D. Okay, but you cannot draw a 30D coding space on paper, right? So we intentionally draw it into two dimensions. You can assume, okay, in this particular case, imagine this coding mu and the sigma are both two-dimensional. Okay, but of course, like in reality, okay, this coding, this mu and the sigma dimension should be much higher than 2. Okay. Okay, but anyway, okay. So because they are assume they are I mean they have their dimensions too. So they will map the input, each input into a two-dimensional input space, right? And this mu and the sigma basically represent, okay, the mean and standard deviation of Gaussian distribution. Okay, if you are not comfortable with Gaussian distribution, I mean there's another name to that. I mean it's normal distribution. Okay, basically like it should be like one of the most commonly used distributions in the world. Okay, and then okay, so once you represent this input instance into a Gaussian distribution, okay, then what decoder does, okay, again it's a very special. It doesn't directly use the mu and the sigma here. What happens is that, okay, the decoder will sample a point from this distribution, from this Gaussian distribution. Okay, so say if the original instance happened to be here, but you can see, okay, the sample that decoder get, okay, may not be exactly the same as the input instance. Okay, so for example, it may get this point here, and then it's going to, somehow transform this point, okay, back to its original shape. Okay, so this is what we call variational autoencoder. So you can see that, yes, when you have fixed input, say if you put this same input twice, you will get the same coding mu. You will get the same mu and the same sigma. Okay. In other words, your Gaussian distribution will be the same, but because the decoder each time it's going to sample from this Gaussian distribution, and because the sampling, because it's a sampling process, right? So the result may not be the same for each time. Okay, so there's a certain probability involved in this sampling process, right? Okay, so after it gets that point, it converted back to the original instance. I mean, it may not be exactly like the input, okay, and also the same input may produce a different output. But of course, they should be similar. They should look similar to input, but it's just they may be slightly different in certain ways. Okay, each time. Okay, so that's what the variational autoencoder, the concept of variational autoencoder, and so as I said, it produced codings which look as though they were sampled from simple Gaussian distribution. Okay, so so how do we use variational autoencoder as a generative model? Okay, actually, okay, because this one, okay, the encoder basically creates sigma and the mu for you, right? But once you have this, encoder and the decoder well trained, okay, you do not need to use this encoder for data generation. You just randomly generate the mu and the sigma, and to sample, well, you can probably just say you just randomly get the sample from your input space. Well, I probably should say this one, from this space. Okay, we call this one as a latent space. Okay, latent space, which is if this is original input, this is the conversion. Okay, and we just randomly get point from this latent space, and we are able to recreate the original data anyway, right? So no matter how many instances you want, you just try to randomly sample from this space, and this decoder is going to do the magic for you to create the data. Okay, I mean one instance for each random sample. Okay, so so variational autoencoder. In variational autoencoder, the more important part, okay, if you want to use it as a generative model, then the decoder part is more important. Okay, and so let's look at the cost function in this variational autoencoder. Okay, of course, again, it's also composed of two parts. You need to make sure the reconstruction is accurate. So you still have a reconstruction loss. Okay, but now, okay, we want to have a second part. Okay, which is to make sure that the second part is called latent loss. Okay, we want to make sure the autoencoder to have codings that looks as though they were sampled from a simple Gaussian distribution. So basically, okay, we are going to compare the distribution, okay, of the transformation with the Gaussian distribution. How do we compare two distributions to find the similarity? Remember, we just talked about a great tool for that, right? KLDivergence, right? That's the actual, primary application of KLDivergence, which is to measure how close two distribution is. Okay, so the KLDivergence used as like in the previous example, as I said, even though okay, we could use KLDivergence in that place, but that's not the primary application of KLDivergence. Okay, but this one is the KLDivergence primary application because we are trying to compare two distributions and see like how we try to push these two distributions together as close as possible. Okay, so we need to measure the difference between these two distributions and then punish the model. Okay, punish the or increase the loss. Okay, when these two distributions are different, right? So again, you see this the Gaussian the KLDivergence between the coding and the Gaussian distribution. Okay, so which result in the loss, the latent loss, to look like this. But sometimes, we want to convert this thing, okay, into something that's easier to compute and which actually also make the model like easier to converge. Okay, basically, we can somehow like replace log sigma square to be gamma. Okay, and then with that replacement, okay, the original formula become like this. Okay, there are only two places that need to be changed a little bit. Okay, so I think like this thing is pretty straightforward. I don't think I need to go over that, but so once we have that, okay, let's have a look at this example. Okay, again, we are using. Okay, so we are using fashion MNIST as an example. Okay, and we try to create a variational autoencoder for fashion MNIST. So before we do that, okay, we try to create a sampling class. Okay, so this one will sample from a Gaussian distribution for us. Okay, and of course we assume there's like mu and the sigma, okay, that are already given, but we don't use sigma directly. We use mu, but we don't use sigma directly because we already define sigma to be, gamma to be log sigma square, right? So if you want to get sigma, you have to use a gamma to get a sigma. So this one looks slightly different from what you may expect it, okay? But that's because like we don't use sigma, we use gamma here, okay? And then we can create an encoder, okay? But we used to use sequential API to create a autoencoder, but now, okay, we could, of course, we could also use a functional API to do the job. Okay, so this is like we use a functional API to do it. Okay, so coding size is 10. So that means like we convert all these input spaces into 10 dimensions in here. So each point is a 10 dimension stuff. Okay. And then, okay, the input is still, okay, 28 by 28, right? So you take this input, okay, and you flatten it, okay, and you call that Z. And you take Z, and then you connect that to a 150 neuron, a layer with 150 neuron, and with serial activation. Okay, you still call that Z. Okay, and you connect this layer to another layer with 100 neuron, serial activation. You still call that Z. Okay, and then okay, you connect that to the coding layer. But the coding layer, as I already mentioned, we need to generate we need to generate two vectors. Okay, the mu, vector mu, and the vector sigma, right? Okay, so we have this, okay, coding log var. Oh, by the way, we don't, coding mean, okay, so it's for the mu, okay? And so it's a coding size, so the mean is like a 10 dimension. And this coding log var is like, well, it's an indirect representation of sigma. Okay, I think you know that already. So again, this 10 dimension. Okay, and then we put this together. Okay, and they call this as a coding. Okay, and then we put this whole thing together as a variational encoder, okay, which is, it takes the input, okay, input equal to input, output equal to this codings, mean, codings, log var, as well as codings. Actually, you only need the third one, because third one contains the previous two, okay, but, we just put them all here, okay. So that's the variational encoder part, okay. And for the decoder, that's pretty straightforward. Okay, so we basically we just need a code. We just make sure the shape is coding size, which is 10, right? And then here, okay, we get this decoder input as an input here, and then we try to connect to 100 neuron serial activation, call it as X. And we use the X as input. We connect to 150 neuron. Serial activation, we call that X again. And we then connect the X into, 28 by 28. And this the reason we call it, we use sigmoid. Again, let me repeat, okay? Because we treat each pixel as like a binary classifier, okay? And then, okay, we call this X again. And then we reshape this layer into 28 by 28, okay? And this is a variational decoder. So the input is decoder input. The output is output. And then we can combine the encoder and the decoder together, okay, to form our variational autoencoder, okay? But you can see the variational encoder, okay, when it gets input, it's going to output something like this. And then we don't need the previous two parts. We only need the third one, the coding. And we put the coding into the decoder. We get reconstruction. And then we put them together, we get a variational autoencoder as chaos model, input equal to input, output equal to reconstructions. That's it. Okay, we ignore the first two outputs of the encoder, as I mentioned. Okay, And we also have to add the latent loss and the reconstruction loss together, okay, as in the loss function. So latent loss equal to negative 0.5 times all this. Okay, it's complicated. I mean, it's basically just this thing. Just this thing. Okay, that's the latent loss. Okay, and we use gamma. We use gamma. Okay, we have log, the coding log var means the gamma. Okay, and then we compile the model. Okay, the loss will be binary cross entropy. Okay, and let me see. Oh yeah. Before this, we actually add this one. Variational autoencoder add loss. We add this thing. Okay, this one and this one in here. And then, okay, we use binary cross entropy. Optimizer we use RMS prop. This one is a little bit special. Okay, you will see that. Okay, for certain reason. Okay, the generative for generative model. Okay, we normally use RMS prop instead of for example, like Adam or like the other type of optimizer. Okay, normally for some reason, I mean the RMS prop, I mean, for work better for generative model. Okay, so okay, the thing that I probably need to explain a little bit is that this divided by 784. Why do we need to divide? I mean, you can see this part. I mean, is just like a. I mean, it's nothing new for this for this equation. But here, okay, we need to divide the latent loss by 784. Why? Okay, it is because, okay, this latent loss, okay, represent the sum of all like 784. Remember, it's 28 by 28 pixels, right? Okay, 28 by 28 pixels. So so totally we have 784 pixels, right? And we treat each pixel as the binary classifier. So we use binary cross entropy, right? And so this binary cross entropy actually consider the loss for each pixel. Okay, but as I said, okay, this latent loss is going to compute the latent loss for the whole 784 pixels together. Okay, so in order to make sure, I mean, you are considering one pixel, okay, at all time. Okay, so you have to divide this latent loss by 784. Otherwise, I mean, when you consider two losses, one is like the latent loss, which represent the sum of all 784 like loss. The other one consider only the loss of one pixel. You cannot add up these two losses together. I mean, they are like orange and apple. You cannot do. They are not comparable. Okay, so basically, I mean, that's why we have this divided by 784. Okay, so just want you guys to be aware of this. Okay, so then you can basically like train this model. Okay, basically use like a fit function. So we train this model for 50 epoch. Okay, and well, so you have a variational autoencoder, and we can use variational autoencoder to generate images that look like fashion items. Okay, all we need to do is sample random codings from Gaussian distribution and decode them. Okay, so you can see here, okay, we just, this coding equal to tf.random.normal, okay, we just obtain like a, 12 random number, okay, from this normal, from normal distribution, which is Gaussian distribution, okay, and because it's coding size, we have, each coding size is 2, right? We have mu and gamma, right? Okay, so we have like 12 pair of random number, sampled from the Gaussian distribution, okay, and then in this coding, and then we put this coding into the decoder, and then we just generate the image. So let's have a look. Of course, I mean, if you really try to do this yourself, I mean, the 12 picture you generated may be different because, well, I mean, this is random. We are getting 12 random numbers here, right? So just want you to be aware, okay? They look like what we have in the Variational MNIST data set, right? Sorry, it's almost like 2 o'clock. Okay, that's well. So you can see that this variational autoencoder is put into work. Okay, and we have we could have more application of this variational autoencoder. Let's take a 10 minutes break. When we come back, we will continue the discussion of this.